Hello, everybody. So welcome to Land Atmosphere Interactions and Boundary Layer Meteorology. This is Professor Amos Tai here. My research work a lot on land atmosphere interactions and a little bit of boundary layer meteorology. And Andy has done a tremendous amount of work on boundary layer meteorology as well. So hopefully during this semester, you're going to learn together with us these very important topics that are really relevant for many of the phenomena that we observed out there, because we actually live in the boundary layer, all right? So most of the weather, climate, or air pollution, atmospheric chemistry phenomenon that we see day to day have direct relationship with boundary layer processes, okay? And we are basically going to study those processes that happen within the boundary layer, especially at the land-atmosphere interface, in order to understand many important topics like how air pollutant can be dispersed and why temperature would change in such a way on a day-to-day basis or within a day. There's different kinds of question, okay? So, and we have got two teaching assistant, Perry Ma and Ben Lloyd. So, Perry, you can say hi to everybody.
Hi all. So
Andy is
I'm
here.
Perry.
Yeah, Andy is here as well, right? Yeah, so hello.
Hello.
Yeah, and is Ben here today as well? No? All right,
No,
so maybe
I don't think.
he will say hi to everybody later, okay? So this is it. I just want to make sure this is, yes, okay, this is being recorded. All right, good. Okay, all right, so this course is going to be divided into three parts. First part is covered by myself. I'm going to go over hydrometeorology, really focusing on the kind of like the individual processes happening at the land atmosphere interface, including an introduction to the physics of the soil, because soil is basically what covered most of the land. So we are going to learn about the physics of that. We will learn about some key concepts in hydrology, because hydrology, the exchange of water between land and atmosphere, will turn out to be very important player in shaping boundary layer meteorology. And we will look at surface energy balance and the relationship of that to mesoscale circulation. And then the second part will be covered by Dr. Ao Yang, Andy, and she will cover basically really like a formal introduction to boundary layer meteorology, discussing the important topics of turbulence, atmospheric stability, boundary layer structure, and the techniques that are very important in quantifying turbulence and atmospheric stability and exchange within the context of boundary layer meteorology. And I will cover the final part, biometeorology and other topics. Basically, it's more like application of all of the materials that have been covered by me and Andy before, to apply it to understand more about land atmosphere fluxes of, say, different chemical species, understand how ecosystem exchange occurred in the land atmosphere interface, and urban climatology and air pollution meteorology as well. So these are more like application topic, applying what we have learned before to understand more specific phenomena. So this is the course outline. So we'll start today's lecture material. So today, what I'm going to do is to introduce some basic concepts, what we are really trying to learn in this class. I'm going to introduce to you flux as a unifying concept. If you have taken my courses before, probably I've already talked about fluxes. So here we'll sort of bring it up again, because flux turns out to be very important, kind of like a unifying concept in land atmosphere exchange and boundary layer meteorology. And then we'll start really the focus of today to understand soil, okay? So we will understand how we characterize soil, what are the different composition of soil, and also how do we quantify the temperature of soil. And next lecture on Thursday, we will dive a little bit deeper into how water actually moves in soil, okay? So that would be really the important key fundamental concept starting in this class. All right. So This class is really about atmosphere boundary layer. We're concerned about it because this is exactly where we live. And a lot of the phenomena that we observe day to day, right? Like, a convective cloud being formed, and then convective rain being formed, and basically the temperature that we are feeling right now, they are all shaped by boundary layer processes, okay? So for instance, people working at the HKO, they definitely need to know boundary layer meteorology because boundary layer meteorology shape the very temperature and humidity and the weather that we actually feeling on a day-to-day basis, okay? So as opposed to large-scale atmospheric dynamics, which really look at the sort of like synoptic scale phenomena, which of course still affect us, okay? But then when we study the boundary layer, usually we would take the synoptic scale meteorological processes as a given, and then we will try to understand how larger scale circulation dynamics would then, as boundary conditions, would affect the boundary layer to affect the kind of things that we actually feel every day, hour to hour. So where is the atmospheric boundary layer after all? It is basically like a thin layer of air that is, well, it can be just a few tens of meters to a maximum of about 4 kilometers, okay, nearest to us, basically just above the surface. But on average, this is about 2 kilometers. We call it the planetary boundary layer or atmospheric boundary layer, basically the layer of air closest to us, which is usually separated from the rest of the troposphere from above, separated by what we call a capping inversion. We are going to learn quite a bit about what the capping inversion is. Basically, it is like a dramatic increase in potential temperature that makes this capping inversion layer really stable. Okay, you will learn a lot more about stability from Andy later. Okay, so here I'm more descriptively, you understand that usually the boundary layer is topped by capping inversion, usually a increase in potential temperature with height that becomes very stable and basically separate the rest of the free atmosphere from the boundary layer. Okay. And then above the capping inversion is basically the free atmosphere, all right? And most of the physics here is, most of the wind here would be in geostrophic balance, all right? If you remember that term from 2020, okay? But in this class, we will focus a lot more on what is happening within the turbulent boundary layer. And we will, of course, understand what the term turbulent actually means. So again, this part basically so this is in meter. This is a scale which is in logarithmic scale. So this is about 10 meter, 100 meter, 1,000 meter, which means about a kilometer, and then this is like tens of kilometers. So basically anywhere between a kilometer to about 10 kilometers, this is the free atmosphere or the free troposphere that we are talking about, the free atmosphere that we are talking about, mostly in geostrophic balance. And these basically below 1 kilometer or 2 kilometers is where we are trying to study, right? The atmospheric boundary layer, which is still divided into a few additional layers. So this whole part is the boundary layer. But then within the boundary layer, we can divide it into two parts, the outer layer or the outer boundary layer and the surface layer. So the outer boundary layer, especially during the day, usually would have relatively uniform profiles of everything. We are going to see a couple of profiles later, and you would know what I mean. And as opposed to the surface layer would usually have a very dramatic sort of gradient, vertical gradient or vertical slope of different quantities, including temperature, humidity, or chemical concentration. So the surface layer is where we live. We will study the surface layer quite a bit, especially in Andy's part. And you're going to learn that usually for the surface layer, the fluxes, we can usually assume that fluxes are constant throughout the surface layer. And you're going to learn more what that means and how do we make use of that fact to derive formula for turbulence and land atmosphere exchange. okay? So this is the surface layer. And the surface layer is usually just a few tens of meters above us, okay? Usually within 100 meters. So this is really the closest layer to us. And a tall building can easily be above the surface layer indeed. So, but within the surface layer, we can also quantify a sublayer called the roughness layer. The roughness layer is usually where the roughness usually is. Roughness meaning anything that causes friction. So it can be the grasses, it can be the trees, it can be the buildings, it can be, like small little mountains and things like that, all right? So anything on the Earth's surface that causes friction, we would call them the roughness element. And the roughness element would basically give rise to what we call the roughness layer. The physics within the roughness layer is actually very complex, and a lot of people have to do like computational fluid dynamics in order to understand it. But from the perspective of boundary layer, we actually do not really study the physics within the roughness layer. Indeed, the roughness layer usually is just treated as a boundary condition again, all right? So it's kind of interesting. For large-scale atmospheric dynamicists who study the troposphere, who study the outer layer, the free atmosphere, like Francis, boundary layer is really a boundary conditions for them. But for us who study boundary layer, all right, the free atmosphere is the boundary layer for us. It's the boundary conditions, and then the roughness layer is also our boundary condition. So we usually just assume the kind of things that we usually just, if this is a grassland, if it is a trees, if it is building, then we would just specify them and with some specific values for their roughness or friction. Okay, and then we don't really look into the physics in between these roughness elements. So to make sure you understand, we are not exactly studying the physics within, around the buildings or like between the trees, that sort of things. Okay, those are really computational fluid dynamics topic. Instead, what we are going to study is, given the roughness layer and given what happens above, what is really happening and going on within this layer, the whole boundary layer, okay? The surface layer and the outer layer, all right? That would be the key of today, of this course. So we care a lot about the profiles of different physical and chemical properties or states. For instance, you can see here that temperature or potential temperature, Q here is a specific humidity, and V here is wind. All of these variables would have some very characteristic profiles or vertical gradients within the boundary layer. So here, this is the FA here is the free atmosphere. So this is more or less like the capping inversion, or we call it the entrainment zone in the daytime. So you can really see that temperature generally goes like this. It decreases with height. Potential temperature likewise decreases with height, but then usually stay constant within the mixed layer or the outer layer. And likewise, wind or humidity is generally relatively uniform within the outer layer or the mixed layer, but then they would have very large gradients, right, within the surface layer. So this is what I have mentioned in the last slide. Okay, but the key point here really is the boundary layer undergoes very strong diurnal cycle, all right? From the daytime profiles of things and the nighttime profiles of things can be really different. And that is very characteristic, and that is very distinct from the free atmosphere. Actually, the free atmosphere does not exhibit that much diurnal variation, like at nighttime, daytime, the wind, more or less, they're very similar, okay? It's really within the boundary layer where things have strong diurnal cycles, okay? They can be very different in the daytime and at the nighttime. And you will learn quite a bit what processes exactly shape the boundary layer, shape the profiles of these quantities, okay? In the day versus at night, mostly in ND's part, okay? Here, I would just mention that all of these vertical profiles of meteorological variables or chemical concentrations are largely shaped by the exchange of energy, momentum, materials between the surface and the atmosphere. And of course, they exhibit strong diurnal cycle, especially on land, because the solar heating on land would be very, very different in the daytime versus the nighttime. And because the boundary layers sit right on top of the surface, the boundary layer is very much dependent on the kind of heat exchange and momentum exchange that is going on with the land surface. Okay, so I will talk a lot more about all of these exchanges throughout the next few lectures. Okay, all right. So indeed, what we are going to learn a lot about is exactly these kind of exchange, right? Exchange of energy, momentum, energy including radiation and heat, momentum, and materials, okay? And what are shaping these exchanges. So let us bit by bit dive into it. So what kind of exchanges are we talking about? Energy, momentum, and materials. Okay, so let us look into it. Usually these exchange processes can be divided into two types. We call it biogeophysical processes. What are they? You have physical here basically meaning physical exchange, okay? Exchange of physical quantity like momentum, water, and energy include heat and radiation. Between the surface, usually that would consist of soil, vegetation, water body, and the atmosphere. So what we are really looking at is like, what kind of processes exchange, how is momentum exchange between the air and the surface, okay? And you're going to learn that this is basically the cause of turbulence. We're going to learn about a radiation exchange, okay, and what shaped them, okay, and the kind of heat exchange that occurs. And you're going to learn that the energy exchange actually determine the surface temperature. And other kinds of processes that are important are basically anything that has to do with chemical substances, including like carbon dioxide or any carbon compound, nitrogen, sulfur, phosphorus, between the surface and the atmosphere. Okay, so that would obviously affect atmospheric chemistry, but also climate, because a lot of these chemical substances are greenhouse gases or aerosols that really affect climate. Okay, so whenever we're studying chemical exchange between the land and the atmosphere, we call it biogeochemical processes. Okay, and they are very, very important, shaping air quality and climate at large, because all of these chemicals play important roles shaping, pollution and climate. All right. So you'll also later see that most of these things, except aerosols and greenhouse gases, they're more like passive tracer shaped by boundary layer meteorology. And then boundary layer meteorology would affect the vertical profiles of these substances. But for aerosols and greenhouse gases, their profiles would in turn shape climate and boundary layer mineralogy. So there would be some feedback going on there. But most of the other kind of chemical substances would usually be passive tracers shaped by boundary layer mineralogy. All right, so let's look at them, go deeper into them. So first, let's just look at momentum, okay? My part of the course would not focus too much on it, but basically the exchange of momentum is what, Andy's part is really about. A lot of that is about momentum exchange. So momentum exchange, well, first of all, by the fact that the surface has to have 0 wind speed, but somewhere above the surface in the air, there would be some positive wind speed, okay? There would be some non-zero wind speed. By this mere fact, you know that there would be a gradient of wind, right? Gradient of wind. And whenever there is a gradient in any physical quantity, there would be a natural tendency for an exchange to occur. That's just, general physical laws. Whenever you have a gradient, there would be an exchange, right? Things would like to go from high to low concentration, or high value toward a low value. So basically, if whenever you see, well, what is momentum? Momentum is basically just mass of the air times the speed of the air, right? So given we are always looking at a per unit mass of air, if you have a positive or non-zero wind speed here and zero wind speed exactly at the surface because of the no slip boundary condition, then obviously there's a gradient and there would be a natural flux. Naturally, there would be spontaneously a flux of momentum from the upper layer to the surface. It's always the case. The momentum exchange is not exactly exchange. It's always a transfer of momentum from the air, which has a positive momentum or non-zero momentum, to the Earth's surface, which have a zero momentum. Okay, so the exchange of momentum is always one way, downward toward this toward the surface. And basically, the whole idea is that the roughness of the surface, okay, anything that is like trees or the grasses or the rocks, or the buildings that are really causing friction, would impose a drag or friction on the atmosphere. So you can just imagine whenever air slide through, okay, whenever air blows through the surface, blows over the surface, all right, the surface would drag, sort of like sort of impose a friction, right, on the air above, okay? And at the same time, because of Newton's third law, well, the air is also imposing a stress, okay, on the surface, right? So the air is sliding over the surface, so the air is kind of like pulling the surface along, but the pulling cannot, the surface cannot really move with the soil, move with the air, all right? So it just feels like a drag or a stress, okay, from the air. And at the same time, the air is feeling the friction from the surface. And by Newton's third law, basically, of course, they are just like two sides of the same coins. All right, the stress of the stress imposed by air on the surface is basically just the opposite side of the friction of imposed by the surface on air. All right, it's just basically just two sides of the same coins by Newton's third law. So basically, the atmosphere imposes this stress onto the surface, okay? And this stress, in a sense, is exactly what it means to have an exchange of momentum, right? A stress is basically a force per unit area. And what does a force do? A force is to change momentum. And anything that changes momentum, of course, is an exchange of momentum, all right? It's a flux of momentum. So this stress itself is basically equivalent to a transfer of momentum from the atmosphere to the surface. And that would shape the wind velocities in the boundary layer and creating a vertical wind shear. And you're going to learn a lot about this in Andy's part. It's exactly the vertical wind shear, the vertical gradient, which causes the exchange of momentum or the stress. And also surface heating, all right, basically the land surface being heated up by the solar radiation, okay? These two things together can lead to dynamic and static instability, right? You will learn more about them. But here I just, give you a sort of like a snapshot of what you will learn. And such kind of instability is exactly what causes turbulence. And the turbulence have two basic kind. Mechanical turbulence is caused by the wind shear, all right? A natural tendency for momentum to go from high wind speed to zero wind speed, okay? And this transfer of momentum basically causes or facilitates mechanical turbulence. Or the other way around, you can say the other way around. The mechanical turbulence facilitates the exchange of momentum, right? They are really sort of like the same phenomenon. But at the same time, solar heating on the surface, if you heat up the ground, then the air right above the ground would be heated up, and thus that would have buoyancy, and that would rise. And that rising of air, and then elsewhere there would be sinking of air. That mixing of air is what we call thermal turbulence or convection. So later you'll learn, basically thermal turbulence is just convection, okay? And mechanical turbulence, basically, the mixing that results from exchange of momentum here. So, and here you're going to learn that, well, the study of turbulence is extremely important for the boundary layer because it's the turbulence that facilitates the exchange of everything else except solar radiation, of course. Yeah, radiation doesn't depend on radiation doesn't depend on turbulence as a means of exchange because radiation can actually travel through vacuum anyway. But the turbulence is actually what facilitates the exchange of heat here and the exchange of all of the trace gases. Okay, so that's kind of like the foundation of physical exchange. Anything that requires air to be a medium of exchange. Okay, that would include heat, water vapor, and other chemical concentration. Okay, so you'll learn quite a lot about this, and in my part as well, how to characterize from the wind profiles to characterize the strength of mixing and how the strength of mixing can affect the profiles of heat, temperature, and other quantities in the boundary layer. Okay, so turbulent mixing later you'll see is very important driver of land atmosphere exchange of heat, water, chemical substances, blah, blah, blah. Well, basically just except radiation, really shaping climate and atmospheric composition at large, all right? So even I, as a primarily atmospheric chemist, I have to study turbulent mixing and boundary layer meteorology because that shaped, you know, important things like air quality and ecosystems exchange, so on and so forth, right? But I'll really mostly leave this part to Andy. But well, 3 lectures, basically next Tuesday, I am going to talk more about surface energy balance, okay? Here, I'm just going to give you a snapshot. We will dive into surface energy balance later. So here, I'm just going to briefly mention, we will, we will study about, you know, the exchange of radiation, all right? So incoming solar radiation, you know, and the incoming long wave radiation, mostly infrared from the atmosphere, okay? And the incoming solar radiation are mostly short wave or mostly visible light. So these are radiation that the Earth's surface can receive, have to kind of be counteracted by the outgoing radiation of solar radiation, okay, after reflection occur. So, you know, the surface have some, you know, like the surface sometimes can have snow or can have something that has a bright color that would actually reflect solar radiation. So the part of solar radiation that is reflected would not be absorbed. So you have to take that away from the surface energy balance, all right? Because that is not absorbed by the ground. And then, but whatever is absorbed by the ground would then be re-emitted as infrared radiation, okay? So this part is basically the sort of like the outgoing long wave radiation, okay, from the surface. And this is the Stefan-Boltzmann law. We are going to learn more about this, or if you remember from 2020, we did talk about this a little bit. So basically the radiation, the radiative balance on the surface, all right? And we will learn more about these absorptivity and emissivity. But here, yeah, so this is the radiation balance, but it is not the only thing. Basically, well, the incoming radiation minus the outgoing radiation would be what we call the net radiation. And that, if it is not zero, that, if not zero, would have to be balanced by some additional fluxes. And these fluxes is not radiative. They are actually sort of conducted by air and convected and conducted by air and also the ground. So they would include what we call sensible heat. Sensible heat is basically the heat transfer by either conduction or convection, okay? In a sense, it's just movement of air, right? So if the air above the ground is heated up, then it would rise and then carry the heat away. So that's just convection. So convection of air is a form of sensible heat, or sensible heat is basically the heat that is transported by dry convection. And there would be the latent heat flux as well, because some of the heat available from solar radiation, from the net radiation, can actually be used to evaporate water. And then the evaporated water can be transported to upper atmosphere. And if they are condensed, then they release the energy back. So this is a transfer of energy as well, We call it latent heat flux, okay? Well, don't worry, we will learn a lot about latent heat, during the next few lectures. And finally, there will also be the ground heat flux, because the ground heat, if you heat up the surface, then some of the heat would actually be conducted, sort of through conduction, be transferred deeper into the ground, okay? All right, deeper into the ground, sort of heating up the deeper ground as well. So we call that the ground storage, ground heat flux or soil storage, okay? Mostly through conduction. And indeed, today we'll learn more about this term today, okay? And these two terms we would look into them later, okay? Maybe 2 lectures from now. So you're going to learn that net radiation is not always 0. Usually, on a day-to-day basis, it's not 0. On a longer time scale, over the entire Earth, they may be 0 or close to 0. But for a particular location, okay, in a particular hour, usually this is far from 0. This is usually far from 0, and they have to be balanced. It has to be balanced by heat, latent heat, sensible heat, and ground heat flux. Okay, and this, in a sense, really shape the surface energy. Surface temperature, right? So the surface energy balance basically shapes the surface temperature throughout the day and throughout the season. Okay. So here, just still relatively introductory material. So we are going to see that, well, albedo, the strong heat, we are going to learn about albedo. So how different, sort of different characteristics of the soil can lead to different sorts of albedo, meaning the reflection of sunlight. So maybe trees versus grasses versus building, asphalt road versus, like a white roof, that sort of things, okay? So different kinds of surfaces can have different albedo, and we are going to see how they will affect the surface energy balance. We will look at surface roughness. Again, different kinds of obstacles, like trees versus grass versus buildings, can have different roughness, and thus they would affect or really shape the strength of the turbulent mixing, which then shape, the heat transfer, okay? All right. And you're going to learn that usually the rougher the surface is, the stronger the turbulent mixing would be, okay? So that is, you'll learn more about this. We will also spend a little bit of time covered by me after Andy's part to really see how plants and vegetation really shape those land-atmosphere interactive processes, okay, through the stomata and the what the plants are actually doing, okay? But I'm not going to talk too much about this in this class because, for some students here actually took ecosystems and climate just the last semester. I will talk a lot more about that in ecosystem and climate, okay? But here we still need to sort of include this because it is important for understanding the exchange and turbulent mixing, all right? But not too much. And we'll also look at soil moisture, obviously, because soil moisture really affects how much water can be evaporated, and that affects the surface energy budget as well. So, well, if we study land-atmosphere interaction processes, of course, the biogeochemical processes would be a major player. But we are not going to cover them in this class, okay? This class would mostly, basically, well, almost entirely about biogeophysical processes, okay? The biogeochemical processes would be discussed in ecosystems and climate, all right? So some people have already done that, okay? So all of these things like carbon cycle, reactive nitrogen, aerosols, BVOC, blah, 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 all of these things that are extremely important shaping climate would not be discussed in this class. But if you're interested in them, please take both atmospheric chemistry and ecosystems and climate, okay? So we will have a fair introduction into all of these very important topics shaping climate at large. But this class would mostly be about the biogeophysical processes, okay? And boundary layer dynamics. All right? So yeah, if you don't mind, I will carry on before we perhaps have a little bit of break. So I have introduced, I've introduced you to the concepts, like what we are trying to study and the kind of topics that we will cover in this class. So now let's start the sort of the core material. First of all, flux is a unifying concept. And if you don't mind, I will also sort of go over it relatively quickly because, well, 2020, ESSC 2020 is actually a prerequisite for this class anyway, so you should have some concept about what flux is. So I will just like relatively briefly mention it. So flux is really a unifying concept for land atmosphere exchange and boundary layer meteorology. We are always talking about fluxes, okay? It's the fluxes that affect the state of the atmosphere, okay? So fluxes are kind of like the input into the atmosphere or the output from the atmosphere. And the quantity of the fluxes, the rate of change of all of these things would affect the state of the atmosphere, the physical and chemical state of the atmosphere. So flux is formally termed flux density, right? Well, they're the same thing, which is basically a flow of anything like mass, heat, or momentum. We are basically studying these three physical things, all right, or chemical things: mass, heat, momentum, per unit area, per unit time. So it's basically just something, all right, a flow of something per unit area of the land surface or the ocean surface for that matter, basically the surface, okay, per unit time, maybe per second or per day or per year. And it is basically equivalent to the velocity, the vertical velocity, I should say, multiplied by density, okay, of that thing, mass, heat, or momentum. So one of the sort of like the most prominent example of a flux is a mass flux, which is basically quantified by, exemplified by the fixed first law of diffusion, okay? So diffusion, this term you may have heard from other classes, diffusion is essentially a flux of mass, okay? And that flux of mass is driven by a concentration gradient or density gradient, okay? So a net flux usually occurs in the direction opposite to the gradient of its density. So if there is like a mass gradient, then there will be a mass flux. If there is like a energy gradient, heat gradient, or basically temperature gradient, there will be a heat flux. If there is a velocity gradient, there will be a momentum flux. Okay, so that is the key concept. Mass gradient leads to mass flux, temperature gradient leads to heat flux, and well, water vapor different gradient would lead to latent heat flux, and wind gradient or velocity gradient would lead to a momentum flux. Okay, so this is all basically the same kind of physical concept. So the first example, of course, is the fixed law of diffusion. A flux of mass, for instance, is quantified to be the negative times something called the diffusivity. It is kind of like measuring how actively diffusing the thing would be, times a gradient of the density. Here is the mass density, okay? But it can be other things. So here you go, you know, if you have basically just from this, you can see that if there is like a concentration gradient, for instance, more mass here, less mass here, okay, then the concentration gradient would be going down in the x direction. So this term would be basically negative, right? If this term is negative, there is a negative here, then the whole term is positive. So there would be a net positive flux in that direction, right? In this direction, in the positive direction. So this basically captures the concept that, well, particles just flow from high to low density or from high to low concentration, right? Something that you must have seen in other physics or chemistry classes anyway. So that's the flux. Here is something that have not been covered in your previous classes. The fixed first law, well, obviously there would come the second law as well. So fixed first law quantify a flux. But a flux is a flux, right? What you're really concerned with is the rate of change of a physical quantity, be it mass, energy, or momentum, okay, over time, okay? And that rate of change of things over time would be controlled by the fluxes in and out of a certain volume, okay? So basically, fixed first law, quantify a flux. And then fixed second law, try to quantify what happens or the rate of change of something given the fluxes, okay, into and out of a particular volume. So fixed second law of diffusion basically combines the first law, right, the flux, and mass conservation to relate the rate of change of density. Maybe, well, if here we focus on mass first, but the same concept basically apply to energy and momentum as well. Rate of change of density, mass density, in a fixed volume, all right? Let's say the fixed volume is a delta X, delta Y, delta Z, okay? To the spatial gradient of the diffusive flux, okay? So you would have an influx here and outflux there, okay? So the outflux minus influx would be the net flux. And of course, the rate of change would be dependent on it. So now we want to derive a set of equation that, a single equation that can quantify this, the rate of change of density per unit time. Oh, by the way, so here, this is, well, just to make sure you know, so the thing is here is that, let's say the volume here, so the mass density here is rho, okay? But maybe the rho here, sort of seen upstream, and the rho downstream may be different. So we can actually have to capture that difference. If they're exactly the same, then the influx and outflux should be the same as well. So there is no point, there would be no change at all, okay? Well, of course, U can be different, but yeah, that's not what we're talking about. So here, so the rho here may actually be different from the rho here, right? So let's say rho here is rho X, and rho here is rho X plus delta X, right? And there may be different, and it's actually the difference in rho that actually drives the changes in, the change in rho within the volume, okay? So now what we are interested in is the rate of change of the mass, okay? Let's focus on mass here first. The rate of change of mass, of course, mass itself is just rho times the volume, right? So with density times the volume is the mass. So the rate of change of mass, of course, has to follow the first law of mass conservation. Well, and that is basically just influx of mass minus the outflux of mass. That's just that, okay? It's just, you know, the influx. What is the influx? The influx is, Fx here, okay? So Fx here times, and the flux is per unit area, right? So the mass flux in total across the whole area here should be this flux times the area here, okay? Oh, if you don't see the cursor, please let me know, okay? Let me know through the chat. Oh, by the way, you can always ask question right away in the chat, all right? So please feel free to ask question in the chat room. So outflux here is the same. Outflux here, I designated F at X plus delta X, okay? Well, this is not times, it is F at, as a function of X plus delta X, okay? So here, the flux here, of course, this is a per unit area, so you have to multiply it by the area here, which is delta Y, delta Z, okay? So this is the influx, total influx, and this is the total outflux. Here, we are only considering one direction, okay? And this result can be generalized to all three dimensions as well, right? But then here, I'm assuming the only fluxes happens in the X direction. So now, the next step, well, the volume here is a fixed volume, so you can just move this out, okay? And then you can also see that, you can just so the whole thing move out here. And then, so this is basically the volume times the d rho dt, okay? Equals to the difference in the flux times the area. And here you can already see that, you can actually, this basically just cancel each other out here and there, right? Okay, and then this whole thing can actually be just put down here, okay? So what's next is, all right, so basically d rho dt, okay, can be equals to, you can, I also kind of just swap between the two things here and add a minus sign in the front, okay? You can always do that because, you know, fx minus fx plus delta x is just equals to negative f at x plus delta x minus fx, okay? So you just do it like that, and you have a delta x downstairs. And for those who have a sharp, a sense of mathematics or calculus, you immediately recognize that for delta x that tends to 0, right? This is basically just the definition of a derivative, the derivative of df dx. Okay. All right. So here you already know that d rho dt can be equals to negative df dx. All right. So, and now, okay, so basically is the, well, we call it the flux diversion, by the way. So it's the flux diversion. So the rate of change of density within a fixed volume is basically just the flux divergence. And here, let's apply the first law as well. We call that the flux itself is equals to negative d rho dx. Okay. You can just substitute this inside this here there. Okay. And the negative sign got canceled out. So you can have the equation d rho dt equals to d dx, the whole thing, d rho dx there. Okay, just substituting this, the first law, fixed law, into the f here, and then you will define this here. Okay. All right. So now, well, this is quite interesting because you are actually having d rho dt here and some second order derivative of d rho dx, okay, with respect to x, second order, okay. And again, if d is spatially homogeneous, at least in x, in the direction of x, okay, all right, then, well, spatially homogeneous meaning it doesn't really change in that particular direction. It's kind of like a constant. Then you can pull this out, and then d rho dt is basically just equals to d, the divisivity times d squared rho over dx squared. Basically the second derivative of rho with respect to x. And now you have a partial differential equation to solve, all right? Okay, so for most practical purposes, when we apply this to soil or air in the model, usually we just solve it numerically, okay? But of course, if D is truly spatially homogeneous, which is usually not the case anyway, but if it is really spatially homogeneous, then you can just theoretically, analytically solve this equation as well. Okay. All right. So now, well, the important point is try to remember this. This is a partial differential equation with respect to both t and x. Okay. All right. And this is a generic form of what changes the density of something. You can basically, if you substitute t here and add some constant, and then this becomes a thermal conductivity and things like that. You're going to see this later, actually today, okay? And basically, you can use it to solve for the temperature profiles or the temperature change of any solid, including soil, all right? If you substitute this to become basically u, for instance, wind speed, okay? And this becomes the viscosity, and that becomes the, usually that we are concerned with the z direction. If this is velocity, then you are basically looking at the Navier-Stokes equation, but with all of the other terms gone, okay? You only have the viscous term remaining, all right? So this is actually a very generic form of sort of like formulation that can appear anywhere. Because in most of fluid physics that are relevant for atmospheric science, most of the time we are talking about conservation of energy or mass or momentum, okay? And most of the equations are derived kind of in the same way, okay? So you will see things like this again and again in the future, all right? So today we'll come back to an example where we can directly use this. And let me clear all drawing first. Well, okay, so what we have, so the fluxes, we have got the fluxes, right? But the fluxes actually require that if we directly use the fixed first law, okay, or even the fixed second law, okay, in the atmosphere or whatever, okay, you basically have to have the spatial information of density or mass density or temperature or moment or wind speed everywhere, okay, in order to understand the evolution of the system, right? So you need d rho dt, you want to know d rho dt, and you need to know, d rho dx or d rho d square rho dx square. You need to know this. You basically need to know the spatial distribution of all of these quantity before you can know the rate of change and the time evolution. And very often, these are not available. Such spatial information, detailed spatial information is usually not available. It may be available for soil in one dimension, but it's usually not available for the atmosphere in general or the boundary layer. So what we usually do instead to quantify the fluxes across the surface and the atmosphere, we would usually generalize the Fick's law for various kinds of biogeochemical and biogeophysical fluxes involving the atmosphere in terms of, instead of a gradient, we look at the vertical difference only, one minus another, okay, in a related quantity, quantified, and then modified by a conductance, which is kind of like diffusivity, but conductance can actually carry a lot more information, physical basis than just diffusivity. So conductance, okay. So instead, what we usually do is we quantify a flux semi-quantitative and semi-mechanistically, semi-empirically to be Cg phi s minus phi a without a. We can quantify, it is basically just a generic, generalized version of the Fick's law. You're still talking about a vertical difference in something, all right, gradient in something. But here, you just look at the difference and you try to capture everything. You try to find the difference, vertical difference in some quantity between the land surface and a reference height in the atmosphere, okay? Later, you will see that the reference height is either 2 meter, 10 meter, or 30 meter, okay? So you'll see that very often across the whole field, we like to measure things at a particular height so that everybody, when they talk about a flux, we're always talking about a flux in between maybe the land surface and 2 meter height or land surface and 10 meter height. So later you'll see the reference height actually becomes very important because if you want to quantify the flux, you actually need to know this, like the fundamental, the Fick's law needs you to know d rho dz, okay? You need to know the entire profiles, but no, we don't really have that information. So instead, we just fix a height, and then we measure the difference from that height to the surface, okay? So the reference size is actually very important. Usually we choose 2 or 10 or 30 or 50, sometimes 50 as well, okay? So this flux of X, whatever it is, into the atmosphere, okay? So this is basically a quantity related to X evaluated at the surface. This is a quantity related to X evaluated at some reference height, okay, in the atmosphere. Again, usually 2 meter, 10 meter, or 30 meter, or 50 meter. G here is kind of like diffusivity, but we don't call it that because it encapsulates much more than diffusivity. We call it the total conductance that encapsulates the differences, the height difference. It can encapsulate wind direction, turbulence, basically a lot of the things that we are going to study in great detail in this class. So total conductance is, here is basically what we will spend a whole lot of time on. And you'll have the dimensionality constant here just to, later you'll see that depending on the units of the things that you have here, you have to convert the units such that the flux itself is a per unit time per unit area quantity, okay? All right, so this is just dimensionality constant to convert. So usually the flux throughout this class, flux is positive if the flux is from the surface to the atmosphere. So for instance, for sensible heat flux, this is basically just temperature. For latent heat flux, this is basically just water concentration or water vapor pressure or specific humidity. So for chemical flux like CO2, then this is just the concentration or partial pressure, if that's a gas. Conductance, again, is something that we are studying a great deal on because it depends on environmental factors like meteorology, vegetation, land surface characteristic. You're going to learn more about this later in this class. And constant C, just make sure that the units on both sides match. Another very important term is resistance. Resistance is basically just the reciprocal of conductance. So conductance is like how large or how effective the flux can be. Resistance is just the opposite, how resistant the system is to build a flux, okay? So it's just the reciprocal of conductance. So R is just 1 over G, okay? So resistance is basically just the flip side of, or the, the reciprocal of conductance. The term resistance is very, very important because it turns out that to quantify land-atmosphere exchange, all right? Because you can imagine from the land to the atmosphere, there are many, many things in between, right? You have the trees, you have the building, maybe a tree is next to a pond, and then you have soil somewhere down there, and then above the tree you would have the boundary layer, you would have the surface layer, all of these things, okay? So you need to be able to quantify all of these things and connect all of these dots together to quantify a common flux into the atmosphere. Because the atmosphere ultimately, right, does not exactly worry too much about what's on the surface. It just kind of cares about what is the overall flux going into the atmosphere. But when we calculate that flux, we need to consider all of the characteristics of the land surface. While you have different kinds of landforms, things like that. So in order to really quantify fluxes, we have made use of a very this is the dominant way to quantify fluxes in basically most weather forecasting models and air quality models right now, and climate models right now, is to make use of a resistance model for land atmosphere exchange or ocean atmosphere exchange. That's the same actually. So the resistance model is basically you're trying to quantify different kinds of resistances, right? And again, resistances are basically just reciprocal of conductances. So you would have basically, depending on exactly where you are, for instance, you have the land surface. The whole thing here is the land surface. Above the land surface, you would have the boundary, or this is, I should not call boundary here. It's like the viscous sublayer, all right? The boundary layer resistance here, it is really talking about a thin layer of air right above the surface, which is usually laminar, right, instead of turbulent. And the diffusion across this boundary, the thin layer of laminar sublayer is pretty much just controlled by the viscosity of the air and the molecular diffusivity of different things, including air itself. And yeah, but above that, there would be basically the the surface layer. Yeah, the surface layer. And the surface layer would have turbulence. So you would have to have to account for the effect of the turbulence. And we do that by quantifying a aerodynamic resistance, which would account for turbulent diffusivity, wind speed, stability, roughness, and we will spend quite a lot of time on this, okay, in the future. Not in these two classes, but after learning about boundary layer meteorology. Basically, this whole thing here is shaped by boundary layer meteorology, okay? Which, together with the viscous sublayer resistance and also the surface resistance, you would then add up all of the resistance together, okay, in a series, okay? So if the different points are connected in series, then their resistance can be added in series, and their conductance will be added in parallel, okay? So this is basically the resistance. The total resistance is basically this plus the whole resistance here. But then the surface resistance is a lot more complicated, all right? Because the surface actually have maybe some part of it is just soil, some part of it is vegetated, and the two are not connected on top of each other. They're actually side by side. So the resistance from the vegetation and the resistance from soil, bare soil, has to be added in parallel like this, okay? So instead of just directly adding them in series, as in the case here, the vegetated conductance or canopy conductance and the soil conductance actually have to be added in parallel. So to add things in parallel, basically the overall resistance is just, you know, R1, R2 minus blah, blah, blah. Well, or the other way to look at it, the conductance actually add together. Okay? So this is kind of really like, okay, you look at the setting of your environment, and then you decide whether things add in parallel or add in series or add in parallel. Okay? All right? So this is even more, and then within the vegetation, within the vegetated land, you would also have different kinds of resistances from stomatal, the cuticular, basically different plant parts. You would have the canopy, okay? And then from the soil as well, okay? So all of these together, when they're added in parallel, you would form what we call the surface resistance or canopy resistance, okay? But the canopy resistance, boundary layer resistance, and aerodynamic resistance add in parallel, are added in series, or on top of each other. So this part is mostly about the turbulence, which we are going to spend so much time on. This part, we are basically just not going to talk about it much because usually it's just one or two equations determined from experiments anyway, okay? So, and it's laminar, okay? It's really about laminar, very thin layer of laminar air above the surface. So this is usually not very important. And this layer is very thin anyway. So this is usually, this resistance is usually very small. And we will spend quite some time on canopy resistance as well, okay? All right. So this is how we are going to, so this is, you know, the way we are going to study them, okay? And we're going to study them in greater detail part by part. All right. So let's see. Hold on for a second. I'm wondering when I should give you a break. If you don't mind, I'll give you a break after 4 more slides, if you don't mind, okay? So I'll give you a break after 4 more slides, okay? So if you don't mind, let me carry on. So now what we have covered is the introduction, you know, what we are trying to study, and flux as a unifying concept, and the way, the framework through which we are studying the flux. And then the rest of this class is really about the specifics, okay, under that framework, all right, under that framework. And we're going to study different parts of that framework in much greater detail throughout the rest of the class. Ultimately, we are trying to quantify fluxes, and it's the fluxes that affect the state of the boundary layer and the dynamics of the boundary layer, okay? And the dynamics of the boundary layer will in turn shape those resistances, okay? So it's all two-way, a lot of feedback mechanisms going on as well. All right, so that's our introduction. Now, I'd like to start talking about soil, okay? So this class is kind of like, let's start from the very bottom and then go up, like gradually go up, okay? So let's start from the very beginning, soil. So let's understand soil because ultimately most of the Earth's land surface is covered by soil. All right, soil actually it's not only the soil that you see like in a forest. Sand is a type of soil, right? So even a rocky, a place that is very rocky, you can still see some soil there, okay? Most of the land is covered by soil, including bare land, including desert, okay? So we want to study soil and understand their characteristics and how we physically quantify the kind of things that, their properties and thus their influence on the fluxes. All right, so we'll study soil texture and composition first. So first of all, soil. What is soil after all? Soil is basically a combination of mineral and organic particles, basically the particles, and they can be mineral, meaning inorganic, and organic particles. Organic usually from the residues of plants and living animals, like basically living things died and then they just, you know, like they become part of the soil, okay? You have learned a lot about that from ecosystem and climate, obviously. Here, let's just take it as a given, no organic soil. Organic and minerals together form the particles. But soil themselves, the particles would have many pores between them. Pores basically means space. We call the space pores because the space is intertwined by particles. So they're like pore. So soil is basically a porous medium, right? With a lot of void in it, right? A lot of space in it. And the space is empty, or the space can be empty. But they're not exactly empty because they're actually filled with something, either obviously air or water. So this soil is usually, this space is usually filled either by air or water, right? So if completely dry soil, of course, then this is really just like shaped by, air. Yeah, but if it is completely soaked in water, fully saturated, then this is filled. Basically, the void is all water. Indeed, for a typical soil, about 55% of the total space of soil, okay, is the solid particles, right? And about 45% are the pore space, all right? I mean, that is even after, basically, it's just like, if you look at a lump of soil, right? All right. So there are actually roughly half of the volume within a column of soil is actually just air and water, basically just pore space, right? Even if you try to compress it a little bit, there would still be space, okay? But of course, we're not talking about compression. We're just talking about natural soil that exists in the environment, all right? So if you dig out a column of soil, all right, then 45% are actually just empty space. So you quantify that empty space, we call it porosity, okay? Porosity phi is basically the volume of the pore divided by the volume of the soil. And here again, soil means both the particle and the space and the void pore space, okay? All right, so this is very important. When we say soil, soil actually means both the particles and the space, all right? So here, V soil here is basically just the volume of the soil column that we dig from the ground, okay? All right, so that is very important to remember, right? The volume of the soil is the whole thing, including both the particles and the space. So we call it porosity. And pore space can be, of course, filled with air and water to various extents. For instance, for mineral soil, well, and then they have different composition. For instance, mineral soil, you would have less than 10% of organic matter. If it is organic soil, then you usually have more than 80% of organic matter. And you usually, based on that, you have three major types of mineral particles. The mineral particles themselves can have three major types: sand, silt, and clay. So you can actually see them here. So yeah, so I mean, like I would love to show you for real, but if it is like a, you know, if it is not exactly a live session, then there's no point of really, you know, I want you to feel the soil actually, but usually in a live lesson, okay? But here it's virtual anyway, so you don't have the chance to feel the soil. So sorry about that, all right? But anyway, so at least you can see it here. Usually it is important. There's sand, there's silt, and there's clay, and they are all minerals. They are all mineral particles, but they have very different forms and structure, all right? Depending on how they are formed, okay, from weathering. So the three types of soil particles, so sand is usually the biggest. You usually have the biggest kind of particle, right? Okay, so if you go to a beach and pick up the sand, you can actually identify individual grains, right? Each grain is quite large. So sand particles are really large, right? The particle size can be up to 2 millimeter, So you can really see it, like see an individual grain, all right, with your naked eyes, okay? Whereas clay is really, individual particles are actually very small, all right? So if you pick up a lump of clay, you cannot really see the individual particle. You just see a clump of things, all right? Kind of like powder, okay? And you can't really identify an individual powder. If you think you can identify something, that's already a cluster of the particles. It's not exactly each particles. So the clay is, yeah, it's like this. Another very important, and then silt is basically somewhere in between, okay? What other things are important? So basically, usually sand particles are roughly granular, meaning they're kind of roughly spherical, whereas clay particle, they can have really different shape, and usually they're more like chips, right? They're more like chips, kind of built on top of each other, instead of individual granular grains, all right? So the clay are very small and usually just like chips tiled up on top of each other, okay? Pore size. Pore size for the pore size of sand particles are usually large, okay? Because basically, you know, the sand particles themselves are large and they're usually spherical, so the space in between them are also large. Whereas clay particles are usually like little chips, so when they are packed together, their pore size are actually small, okay? But the total pore volume, actually for sand, it is lower, all right? Because the sand particles, after all, they are packed together, okay, kind of, and individual pore size can be large, but then the volume of the total pore volumes can actually be lower, okay? Whereas clay particles actually have a lot of pore space, even though the pore size are small, but then the clay particles are actually intertwined in a multi-dimensional matrix in a way that indeed there is a lot of space intertwined in between the particles, okay? So basically, this is more important in contributing to the usually lower porosity of sand particle than clay particles. Clay particles clay turns out to usually have larger porosity than sand particles, okay? So just something to remember, you know, sand particles, even though they're large and stuff, their porosity is actually low, all right? And clay particles actually have larger porosity, okay? Clay particles generally have the largest surface area as well. That would be very important to answer one of the questions later. So it has very large surface area, and meaning that because they're really kind of like small particles cluster around each other with actually a lot of porosity around them, and they're arranged in a way that would have actually a lot of surface area in contact with the pore space, okay? Even though the pore size themselves are small, right? So you actually have a lot of contact surface area for the clay. And that's also partly why the clay themselves hold on to each other very strongly, okay? If you pick up a lump of clay and you just pick up a clump of things, okay? Unlike sand basically, right? Like if you pick up sand and then just open your finger a little bit, and then the sand would just slip right through. But if you pick up a clump of clay, and even if you open or spread your fingers a little bit, the clay would just still stay on top, okay, like a clump of thing. It's really because they have larger surface area in between the particles. So the particles themselves can really have a lot of surface area to sort of like interact with each other, sort of like and the pore size is small. So the particles can actually kind of like closer with each other, and then they can have adhesive force sort of sticking them together, okay? Especially if you have water as well. So, well, of course, you know, you have clay, silt, and sand, but of course, a lot of the soil, you know, when you go to a particular forest, usually you don't only find clay or only find sand or only find silt. Usually, the soil that you see is a combination of all of them. So different soil type is usually quantified by the relative composition or relative abundance of the particle types, which then determines the soil texture and structure. For instance, if you have more clay, then you would have something like sandy clay or silty clay. You have silty loam. But if you have something that is exactly somewhere in the middle, right? If you have something that have some clay, some sand, some silt, that's actually the best kind of soil. We call it loam. So loam soil with a good combination of all particle types is generally considered better for farming. Okay, just some general fact. So loam is actually pretty good, all right? Sand is very poor for farming because like it doesn't retain water. Well, later you'll learn more about the soil property, okay? And clay is also not very good for farming either, okay? Because like they're so, like they stick together too much and they really impede water movement, right? So this is not very good. Silt is a little bit better, but the best is really loam soil. So clay particles and organic matter are really good, what we call cementing agents that help soil particles stick together. So if it is just the clay, then the clay would really be sticking with each other very strongly. That would hinder the movement of water and nutrients, okay? So clay is not very good for growing plants, okay? But clay particles themselves are useful if they are added to, say, sand or silt, okay? So they can help stick the particles together, all right? As so is organic matter. So when they stick the particles together, then the soil particles can be more sort of like a, you know, like there's like at least a chunk because the opposite end would be sand. So sand really just like they don't hold on to each other at all. Okay, so and that would be bad for farming as well. So the best soil is actually you know, a little bit sticky but not too sticky. So as promised, after this one, I'm going to give you a break. So yeah, after talking about soil water content. So soil water content, yeah, so here, very, very important. Well, we are going to go through this like basically today and next lecture on Thursday as well. So we need to understand how we quantify water in soil, because later you'll see, and as most of my graduate students, most of the students that work with me know, soil moisture is an extremely important player in boundary layer meteorology, okay? Soil moisture control how much water can actually be evaporated into the atmosphere, shaping everything like precipitation, clouds, and everything, okay? So how do we quantify soil water content? Soil water content can be quantified by what we call, soil moisture can be quantified by what we call volumetric water content. And indeed, whenever we say soil moisture as a term, usually that means volumetric water content already, okay? Basically, that is the volume of water, all right, total volume of water per unit volume of soil. And remember, the soil includes both the pore space and the particle, right? And the pore space can be filled with either air or water. So now the part of water divided by the total soil volume, theta, right, is the soil moisture or volumetric water content. All right, good. So simple. Next. So very important. Porosity, as we learned before, is the total amount of space. You cannot have a higher volume of water than the volume of void space, right? Right? Because you know, you just can't have that. You know, the maximum amount of water, the maximum volume of water that can be held by the particular soil is the porosity, right? Yeah, if this equals to the porosity, basically the soil is fully saturated. There's no air, no gaseous air in the soil, okay? So the soil is what we call saturated. And later you'll see this term, basically the theta at which the soil is saturated is basically the porosity. So phi and theta sat is basically the same thing, okay? This is the water content, volumetric water content at saturation, which basically means porosity, all right? Because you cannot have saturation above porosity. So here, So if this is the volume of the soil, okay, volume of the soil, of course, this is not distributed like this. I mean, in reality, the soil is when we quantify something and have a particular soil moisture or content, of course, we assume this column of soil is uniform, right? But you can actually see that here schematically for the soil volume, if 55% of the soil is solid, then the rest, about 45% would be pore space. And the pore space, if it is filled completely with water, then the soil is saturated, okay? And of course, most of the time, the soil is not fully saturated. So we usually have to quantify what we call the percentage saturation, how saturated the soil is, which is basically just, the soil water content, the volumetric water content divided by the porosity times 100%. So this is the percentage saturation. So if there's like no water at all, right, 0% saturation, okay, then basically all of the void space here would be 0, okay, all right, so percentage saturation. Good. So here, very, very, very important concept that probably you have not seen before if you have not taken any class related to land, land or soil. Water content can actually be held in soil even after gravitational drainage. What does that mean? Let's say there is like a volume of water, volume of soil. Indeed, for instance, after it rains, then the whole soil can become saturated. Let's say the rain stops, okay? And then you can imagine water can gradually drain away, right? But even after you wait for a long time, and assuming there's no evaporation or other processes that take away the water, indeed, even after a long time, there would still be water holding on to the soil. That is a very key feature of soil that you should know, okay? Soil has a natural capacity to actually hold water, right? And that would be after gravitational drainage. Gravitational drainage just means that, gravity would just pull out the water, but gravity is actually not able to pull out all of the water, right? So even after a long time and without evaporation or other processes, some water is bound to stick with the soil. And that is really because soil particles themselves has a natural ability to hold on to water, because the particles have charges, right? Can have negative charge somewhere and positive charge somewhere. So there can be cohesive force or van der Waals forces, okay, between the soil particles and water. So basically, soil particles, by these chemical or electrostatic interactions between the particles and the water molecules, soil can hold water naturally after gravity pull out some of them. And the water content that can be held by soil after gravitational drainage is what we call the field capacity, right? Very, very important. Field capacity is actually the amount of water that soil can hold naturally, basically, all right? Okay. So maximum, or I should say maximum, okay? Because, I should say after gravitational drainage, that's the most correct one. So you can see here that for a typical loam soil, the best kind of soil, indeed, the gravitational water is just about 5% volume, all right, of the volume. Indeed, after gravitational drainage, gravity can drain just about 5% of the total volume of water, okay? Basically drain away water, that the volume of that is just about 5% of the total volume, all right? Indeed, the whole part here, all right, which is roughly about 40%. 40% of space can still hold water. The 40% of the whole total volume can still hold water. Indeed, soil has a very amazing ability to hold water indeed, all right? This may not be something that you might have thought about. You always think, oh, soil will just gradually dry, okay? No, I mean, unless you have strong sunshine above. Otherwise, a natural soil can actually hold quite some water. All right. So this whole part, so this here, so if water is here, then if water is, if theta is 0.45, then water is saturated. If theta is about 40, so 0.4, then it has reached the field capacity, okay? But of course, as soil dries, sometimes it will still dry because, for instance, if you have a strong sunshine and then you have evapotranspiration, then the soil will gradually dry because water is being evaporated out and then the water is being pulled back up. So water movement can actually become more difficult as the soil becomes drier and drier, all right? So you can imagine if the sun is, or the plants are withdrawing water from the soil, then water content can actually go down. Okay, but as it goes down, it doesn't go all the way to zero, even at the driest condition. Another important fact that you may not know, okay, in natural environment, even in natural environment, I'm not talking about, you bake up the soil in an oven, then obviously all water will be gone. But if in natural environment, even under the driest condition, usually there would still be some water left in the soil, but that water would be actually unavailable for plants because at some particular percentage of water content, like about 15%, for instance, even though there's still 15% of space that has water in them, or the volume of water is actually 15% of the space, total soil, that water is actually not available for any use or for plants because water by that point would be so strongly bound to soil particles that the water actually cannot be removed or extracted by plants, okay? So that is another important point. Even the driest soil where the plants would die, the soil itself actually still have some water, but this water is unavailable, okay? And that particular point below which water cannot be drawn by the plants, we call it the wilting point because that's exactly where the plants cannot draw the water anymore and then they would die, even though the soil still has some water, which is unavailable for the plants. And we call this point the wilting points, okay? All right. So that is very important. And basically in between the field capacity and the wilting point would be the amount of water available for plants, okay? For instance, after it rains, then the whole soil column becomes saturated, but very quickly, even before plants can absorb salt water, part of it is drained away by gravity. And then the remaining water, part of it is actually not available for plants, however hard the plants try to suck it. So the only available water is somewhere in between the field capacity and wilting point, and this part will be available, right? So now, available water. So now I would like to, look at the exercise, all right? So we are going to have about 2 to 3 exercises per lecture. And usually after after 2 lectures or so, I will go over the exercises, okay? And so I'll go over the exercise, this exercise next time. But here, I would like you to take a break and at the same time, look at the exercise, all right? So please just look at this problem. Here, the problem is about a loam soil about 30 centimeter deep, okay, has a volumetric water content of this and a porosity of this, okay. How much rainfall in total is needed to saturate the soil, right? Basically, how much rainfall do you need, okay, for ponding to occur? Ponding basically means the water would actually go above the soil and you can actually see running water, right? If the soil is saturated, then if you add even more water, then the water would just rise up the soil, rise above the soil, and then you would have a little pond there. So that is called ponding, right? So so you can already see why this is important to understand because you need to predict when flooding would occur, right? So you have to know the water content of the soil at the beginning, the porosity of the soil in order to predict when flooding would start to occur, okay? So here, try to work on it and explain why clay typically have a higher field capacity. It holds more water after gravitational drainage than sand, okay? All right, and I'm going to pause. Okay, all right, so we'll return to the material here, and I'm going to yeah, play this. Okay, so I'm going to go over this later. Okay, this question. So hopefully you have thought a little bit about this, but I will give, basically go over all maybe a few questions together. Okay, so that would be better. Okay, so now, but first of all, I would like to answer Jeremy's question. Basically, because the soil actually have a very deep profile consisting of different layers. Like litters, topsoil, blah blah blah, so on and so forth. So in boundary layer study, do we consider only the top layer or the whole spectrum of soil? So what my quick answer is we actually do consider about the whole column of soil. Okay, as far as they are relevant. Okay, so for instance, we don't only consider the topsoil because in order to calculate what is going on in the topsoil, you need to know what's beneath it, and in order to know what's going on in that sublayer, you need to know what's deeper in between it. Because when we are like calculating water runoff or groundwater discharge, that sort of things, we are really important for understanding water cycle and things like that. With relevance for climate, we do need to know what's happening in the deeper soil. So we basically need to know, theoretically, we want to know everything from the topsoil all the way to the groundwater level, all right, the water table, basically. Yeah, but then it really depends, like on the particular purpose of your model. For instance, for a climate model that I just looked into, it divides the whole soil column into about 15 layers. And then the 15 layers can be more than 10 meter, up to about 30 meter below the ground. Okay, so but most of the layers are actually in the first first few layers of the soil, first few meters of the soil. Okay, so usually it's like in the shallower layer, like within top meter. Yeah, most of the layers are actually in the top meter, and then further down, each layer will become thicker and thicker because they are relatively uniform. Right, so we do consider the whole column of soil right below, above the water table, but at the same time, we also focus a lot more on the layers that is closer to the surface. Okay, and the topsoil, of course, is very important. All right, and Jesse also have a quick question. I have a quick question: is boundary layer resistance same as quasi-laminar resistance? Oh my goodness, good question, and you're totally right. So I really don't like the word boundary layer resistance as in some books, because as if, well, actually, the whole layer of things that we are studying is the boundary layer. And from atmospheric science perspective, the boundary layer is very turbulent, all right? But from other principles, when they say boundary layer, usually they only mean the laminar sublayer or the quasi-laminar sublayer. The laminar layer of air right above the surface. Okay, so when we borrow that term from the other field, actually that's more correct. We call it boundary layer resistance, which basically means quasi-laminar layer resistance. Okay, but you should know that actually the whole layer of air is boundary layer, and most of it is turbulent. All right, so when we say boundary layer resistance, it is not the resistance of the whole boundary layer that we're talking about. It's really just the quasi-laminar sublayer, because we borrowed that term boundary layer from other field. Yeah, that is a little bit confusing. So in a sense, yes, I would rather call it quasi-laminar sublayer of resistance instead of boundary layer resistance. Yeah, that is very good question. So now I'll go over that question, that exercise later, so don't worry about it. Now let's really start to look at some physics, okay? Soil temperature. Soil temperature obviously is very important because the ground heat flux depends on it, and the sensible heat flux also depends on it, okay? So we have to know what controls soil temperature. So let's look at the profile. Usually a typical summer profile look like this. Let's say this is the top soil, okay, about 5 millimeter, okay, just really like the top layer of the soil, basically the surface. You can really see that there is like a strong diurnal cycle, right? A strong diurnal cycle that follow mostly the forcing, okay? So if you have the sun that is the strongest, or the radiation is the strongest at about noon time, okay, then this layer also have a peak at about those time. All right. So this top layer basically follow the radiative forcing very closely. Okay. So if the peak is here, then the temperature is also peak there. Okay. At this time, at around this time. Okay. And very strong diurnal cycle because there is a strong diurnal cycle of the solar forcing. Right? Because the sun go up and then go down. So obviously solar radiation is very different in the day than in the night. So the topsoil also follow the pattern. But the same here at the top, this is the depth, all right? So the topsoil have very large diurnal cycle, like right before sunset, it would be usually the coldest. And afternoon would be, right afternoon, it would be the hottest, okay? That's usually when the strongest forcing is. And this is the coolest at about before sunset, because you have been through a long night of radiative cooling. All right, so this is the coolest usually. But then the interesting thing is if you go down, all right, so diurnal and seasonal range, actually there are some seasonal ranges, seasonal cycle of the surface temperature as well. They are also very predominantly shaped by the cycles of solar heating, okay? But are also moderated by the uptake and release of heat by soil. So I should so here, for instance, in the day, it is really just the solar heating that is dominating it. But in the night, okay, then well, you don't have any solar forcing, okay. So basically, it's the radiative cooling and the release of heat from the deeper soil that has been stored during the day that control the surface temperature. So that's another thing. You can see that the peak can be really high there, but the trough is not too deep down, okay, relative to the average. It's really because, and slowly, the heat that is stored during the day can actually be slowly released back to the topsoil. So the topsoil would still be not too cold, okay? All right, anyway, so yeah, but very, very importantly, but the diurnal range actually decrease at greater depth. You can really see that, well, first of all, well, if you go deeper down, the diurnal cycle actually, the amplitude of the diurnal cycle or diurnal range actually decreases, right? So if you go deeper down, the range is smaller. Go deeper down, the range is smaller, until at a particular depth. Basically, there is very, very little diurnal cycle, all right? So, and this is about 400 millimeter, right? 400 millimeter, basically meaning 40 centimeter. So 40 centimeter is basically just like, I don't know, like this. So even just about half a meter below the soil, right? You already don't have too much diurnal cycle. Okay, so the diurnal cycle actually quickly, the amplitude of the diurnal cycle quickly depletes with depth. All right, by about half a meter. Well, actually here is already by about 20 centimeter. There is like very little fluctuation already. So we want to answer, why does the diurnal range decrease at greater depths? Okay, that's the first question. A second question, if you look here at the peak actually shifted later as you go deeper down. Okay, so at 25 millimeter, okay, the peak is still about the same, but at 5 centimeter, the peak is already like 2 hours later. Okay, and at 40 centimeter, or no, even just 10 centimeter, you would have the peak that is basically even 2 hours later. Okay, so the next question is, why does the peak temperature occur later in the day at greater depths? Okay, well, I mean, when you think about it, well, think about it for a moment. Well, in a sense, you can physically understand it. Well, of course, because it takes time for heat to transfer by conduction. downward. All right. So by the time the heat can reach, you know, a deeper layer, maybe the peak forcing is already gone. So the peak actually occurs later. So that makes sense, right? And and again, well, it takes time for the heat to reach deeper down. And by the time it reaches deeper down, the forcing is already gone. And maybe it's already in the evening, right? And the heat is slowly being released back, right? So the amplitude will be smaller as well. Okay, so physically you can kind of understand it, all right? Like, again, you know, like heat really takes time to reach the deeper soil. So maybe by the time it reaches a particular depth, the forcing is already gone. So the peak will be delayed, and at the same time, the amplitude will be reduced as well, okay? And of course, some of the heat is used to heat up the layer above it, so above a particular depth. So obviously less heat is like, you know, being transferred there. But we don't want to just physically understand it. We want to be able to calculate it, okay? So let us look at some quantitative way to really quantify soil temperature. And of course, we use heat flux. Soil heat flux transfer is analogous to diffusion equation. So again, you see this again, right? So the flux, the heat flux here is a negative times the thermal conductivity times delta T, delta Z, okay? So dt, dz, okay? Which is the vertical temperature gradient, right? So again, here a heat flux is basically just you know, a vertical temperature gradient divided, multiplied by a conductivity, all right? Kind of like conductance. Well, the sign is usually arbitrary anyway and depends on how you want to define it. So here, we just define negative to mean downward and positive to mean upward, all right? So here, if Z, I should really add some drawing here. So if, yeah, if Z is, so let's say this is Z at 0 mm, then here actually Z is equal to, okay, hold on. Z would be equals to negative 5 mm. Here Z would be equals to negative 50 mm. Okay, so a soil layer of 5 meter deep, if we define upward to be positive and downward to be negative, then if the surface we define it as like 0 mm, okay, then this depth is basically negative 5 mm, and this depth is actually negative 15 mm, okay? But usually, well, that's what Z is. Usually we would just call it the depth. Then the depth, of course, is just 5 mm and 15 mm. Right? Just make sure, you know, you get the coordinate system right, okay? So here, if the temperature here is 41 degrees Celsius and the temperature here is 37 degrees Celsius, well, if you just look at the flux, you know that, well, this is higher temperature, this is lower temperature, then obviously the flux is downward, okay? So there will be a net heat flux from here to there. So now, just very quickly, what is the heat flux F? If the conductivity of the soil matter is about 1.5 square watts per meter per kilometer, sorry, per Kelvin. All right. Well, I mean, I'm not going to just, you know, like think about it for a few seconds, but obviously it's nothing more than just applying this equation, right? So here, basically, the whole idea is just the flux itself, right? The flux here is, well, that it's negative K. K is, but kappa. Kappa is this, right? 1.5 watt per meter per K. By the way, always keep the units when you're doing calculation. You would save yourself a lot of trouble later if you are accustomed to using you know, keeping units, okay? Then delta T, delta Z, okay? Well, dt, dz, it doesn't exactly matter whether this is T1 or whether this is T1, as long as you're consistent with both the direction of T and Z. So here, let's say this is T2 and this is T1. So it would be 41 minus 37. Well, Celsius is just the same as Kelvin. You know that? And now Z. Well, you have to use the same, if it is 41 minus 37, then it has to be this height minus this height. So this height is -5 mm minus, this is -15. All right. And then you have mm here, mm, okay? All right. And finally, you have to convert mm into meter, okay? So don't get yourself derailed by not being careful with units. So you have to have a conversion factor. Is there a better way for me to do this? Because it's in the way. Okay, maybe I'll draw it slightly better. Okay, don't mind, I'll just draw it slightly better. Yeah. Okay. And then you would have what? 41 minus 37K. And here you would have, well, this is -5 minus, so this is basically -5 minus -15, right? So this is basically just +15, all right? And then finally, you have a conversion factor. So you want to have meter here, and you want to have millimeter there, okay? So you add a conversion factor to convert mm into meter. So you need a conversion factor, but this is exactly, you know, it should be unity because 1 meter is equals to 10 to the power of 3 millimeter, okay? So now everything is canceled, here is canceled, this is canceled, all right? And then you just add all of these things, all right? And then here there is like a meter per meter per to the power of 1, -1, and here there is like a meter to the power of 1 as well. So you would have meter to the power of 2, all right? -2, sorry, all right? And then you have watts there. And if you calculate it, it's exactly -600, okay? So this is just like, you know, showing you how to substitute, basically substitute numbers into a particular equation to quantify the flux, okay? But this way, I emphasize again that keeping units are very important, and adding conversion factors would be very, very crucial in order to keep track of the units, okay? So that what you get in the end have the right unit and or the right numbers for the unit that you want, okay? So here, yeah, and very easily you have done that. So the next question is actually about, yeah, the next question is really about, well, if the thermal conductivity of sand, clay, or peat and snow, they're all very different from the loam soil that you have just looked at, then what would happen to the heat flux? And most importantly, how does the heat flux in organic soil and snow compare with that of mineral soil? All right, given the small conductivity there, and which material is likely to warm more? So again, I would like you to just spend maybe a few minutes to think about it. We're not going to look at it, okay? I should say we are going to go over it next time, okay? But here, please think about it for a moment and maybe start doing it, okay? All right, maybe start doing it and start to think about how does the heat flux in organic soil and snow compare with that of mineral soil? And if you know that, if you want to try an answer, and you can actually basically put it in the chat room as well. Of course, you can send directly to me or send it directly to Perry, okay? All right, so let me also pause. Yep, so thank you very much for some of the answers. Yeah, so yeah, most of you have got intuition about, you know, even if you just look at the thermal conductivity, you will be able to know which of the materials will warm more, okay, given with a given amount of forcing, okay, for instance, okay, and which material is likely to warm more, all right, and that usually is consistent with what you have seen in reality, okay, because like think about it, if you go to a beach, all right, and let's say go to a beach versus going to maybe some other kinds of soil, okay, maybe the, you know, or some grassland where you have some soil underneath, you know that under a sunny sun, which surface what warms your would really like you would really feel hot, yeah, or even burned by the sand, by the land, okay, so you know which one would actually be heated up more, right? So just think about, you know, what you feel when you're on a sand beach versus maybe a grassland with some grass floor with some soil on it. Okay, so you can really know it. Okay, and we will of course go over it again during the tutorial. So, well, yes, that is flux, the heat flux. So the heat flux, of course, but what we are really concerned with, or what we really want to know, is the rate of change of temperature in soil, right? Yeah, I know the flux, great, but then ultimately what I really want is, given the flux or given the fluxes, how would temperature change over time in the soil, okay? So again, basically, it is just the next step of or equivalence of the fixed second law of diffusion. Now we can also quantify the rate of change of temperature, okay, as a function of the fluxes, okay, and the temperature profile itself, because the flux depends on the temperature profile. All right, so I can actually skip most of the derivation because the derivation is basically the same. Really, the derivation is the same as the fixed second law of diffusion, okay? So here I would just like to draw some parallels. The parallels are just that, or some differences. So here, instead of looking at the x direction, we are looking at the z direction, the vertical direction, okay? So we are considering just the vertical fluxes. So the influx and outflux would be basically just, you know, from the top and from the bottom, okay? Towards the top and from the bottom, okay? And then the change in storage here, instead of basically because we want to find, so F is the heat flux, right? So in order to relate temperature to heat, you have to multiply it by rho and C, all right? Rho is the density of the soil here, and C is the heat capacity of the soil, all right? So rho times C times the temperature would then be the heat, okay? So then later you'll see the units actually work out. So this is kind of like just adding some dimensionality constant to make sure that the fluxes actually are right, okay? So that is exactly what I'm talking about. This is basically just the dimensionality constant to make sure that the fluxes are actually have the right unit, which is joules per meter square per second, okay? And then you have flux in, flux out times the blah, blah, blah. And then, yeah, all of the derivation is the same, okay? The only exception is now it is in vertical direction, and you have to add some extra dimensionality constant to make it a heat flux, okay? Instead of, you know, like there's like no temperature flux. There's only heat flux, and you relate temperature to heat by multiplying the density and heat capacity, okay? Well, I mean, yes. So, and if you do that, you will come up with this equation. Rho C times dt, all right, would be basically dz times kappa. Kappa is the heat thermal conductivity, the dt dz. So it looked exactly the same before, except you have this dimensionality constant here, and you have kappa here instead of d, and you have z here instead of x, okay? So really the same, essentially the same. So if this is a constant, okay, if the soil is homogeneous, and you can basically just put kappa outside and also put rho C down there, okay, put it outside, okay, well, maybe I should draw. You can put this outside if the soil is spatially homogeneous, and you can put this down here as well, okay? Then you will come up with this. all right, dt equals to kappa divided by rho c times the second derivative of t with respect to z. Okay. So now, again, this is a partial differential equation, which I don't expect you to know how to solve. Even though as an atmospheric scientist, if you are, you should be able to solve it. But yeah, I'm just going to give you the solution, okay? So, but this is a very standard partial differential equation, okay? With the derivative to t on one side and derivative to space on the other side. This is basically just a diffusion equation, okay? And if all of these things are a constant, then boom, you can easily solve it. So kappa is the thermal conductivity again. Rho here is the soil density, okay? Rho here is the soil density. C here again is the specific heat capacity, okay, which is joule per kilogram per K, all right? So basically heat capacity is like how much heat can the soil hold per unit temperature rise, okay? So if the temperature increased by 1 degree Celsius, then how much more energy does the soil hold? So that is the heat capacity. Well, rho C together, rho times C together is what we call the volumetric heat capacity, which is great because this is basically just, you know, this cancel each other. It's basically just joules per unit volume of the soil per K. So we call it the volumetric heat capacity. So let's see. All right, let's solve it, okay? Well, I mean, let me tell you the solutions. Oh, sorry. Before that, let's look at some of the properties. So here, I am showing you the thermal conductivity, or kappa. Here, I'm showing you the volumetric heat capacity, which is rho C. Okay. All right. So you can really see that thermal conductivity here is kind of how easy can heat get across a particular distance. Okay. So higher conductivity means heat can go faster, or more heat can go per unit time. All right. Sorry, per unit distance. Right? I don't know, per unit time as well. Okay. Per unit time, per unit distance. All right. So you can see that quartz, which is the primary material for sand, has a really high thermal conductivity. Okay. So you can already feel that why sand heats up so quickly. All right. You know, like on a beach. All right. The sand becomes very hot very soon after noon. Okay. So this is really why, because quartz itself has a very high thermal conductivity. The heat capacity is, you know, okay. Where other materials like clay or organic matter, they have much lower thermal conductivity, okay? They have actually similar heat capacity. So each volume can take up similar amounts of heat per unit volume rise, per unit temperature rise, but they can conduct heat much fast. I mean, quartz can conduct heat much faster. Okay, so these are two different concepts. This is more like how fast can heat grow, or how large the heat flux can be per unit for distance and per unit time. All right, and heat capacity is how much heat can be taken up by a particular volume. All right, they are two different concepts, and the two of them basically, you know, the how quickly something can go, how quickly the temperature rises for the soil really depends on both of them. Okay, because the constants that you see is basically, you know, the constant that you see, right? dt is equals to kappa divided by rho c, okay, times this. All right, so you can really see that, well, higher conductivity usually means that the temperature can go faster, increase faster, okay, upon heating. All right, higher conductivity, it warms up faster. That makes sense, right? But it is counteracted by the heat capacity. So if a material can take up a lot of heat per unit volume, per unit temperature rise, all right, per unit volume as well, then it actually heats up more slowly because it can take up so much heat, right, without rising its temperature too much. So this is really a counteraction between the two things. How quickly can heat be transported, and how much heat it can take, and they are these two things can kind of cancel each other out in terms of the rate of temperature change. But you can see that organic matter, water, or air has really low conductivity. Okay, so more porous soil usually conduct heat more slowly. But at the same time, water can have really, really high heat capacity, whereas air has really low capacity. So you already kind of know that wet soil, okay, can take up a lot more water than, can take up a lot more heat than dry soil, right? But at the same time, wet soil can conduct heat faster than dry soil, okay? So again, you know, the two things kind of counteract with each other. So does wet soil warms up faster or dry soil warms up faster? It is really a counteraction between the two of them, okay? All right, and you can basically just, you know, if this divided by that and this divided by that, and then you know, okay? So it is not like simple. It's not simple. It's really a counteraction between both effects of thermal conductivity and heat capacity. All right, and you really have to do this sum. I mean, do the product. Quotient in order to know this divided by that versus this divided by that, and then you will know the, so to speak, the rate of temperature change. So again, for instance, for different sandy soil, clay soil, or peat soil, you can also see that this is the percentage saturation, how much water it has. So again, of course, more water, higher conductivity, more water, higher conductivity, more water, higher conductivity, because water is a much better conductor of heat than air, okay? But at the same time, more water, more heat capacity, more water, high heat capacity, more water, high heat capacity. It can also take up more heat. So we don't know whether temperature changes faster until you find the quotient. So I would encourage you to actually find the quotient now, maybe, all right, if you have a calculator around, and then you can really compare. You can really tell, okay, does wet soil or dry soil, for either of them, for which of them, temperature would rise faster given the same forcing, okay? So try to just figure it out yourself. The important key idea, I don't want to tell you everything, you know, the key idea is just that how fast the soil can warm up depends on these two factors, which often counteract with each other, okay? But if I ask you a particular question, all right, so on this particular day, the wet soil warms up faster, okay? So then so you have to be able to explain the reason behind, okay? All right. So now let's try to solve the equation, okay? Let me clear a drawing. So now you have this equation, which is a partial differential equation, and this, if all of these are constant, then there is a analytical solution to it, okay? So temporal evolution of soil temperature at various depths is found by solving this partial differential equation. And suppose, I mean, I myself is not, you know, a mathematician either, but I know, you know, usually the way to do it is that you can impose some solution first, and then substitute it in there, and then if it's actually consistent, then that is actually your solution. Well, one of the way to do it. So suppose soil surface temperature, but this form of the partial differential equation is so common in science, in fluid dynamics, in heat conduction, and that sort of things. Yeah, so there's like a standard solution, really. So suppose soil surface temperature is driven by a diurnal solar radiation cycle. So it is basically kind of like the boundary conditions. So you now suppose the boundary condition is the top soil temperature, which is really driven by a diurnal solar radiation cycle, okay, with a period P, all right? So period P is basically just how long the cycle is. So of course, for a diurnal cycle, it is exactly this amount of second, this number of second for a diurnal cycle, okay? So here, basically, let's say, suppose that the surface temperature T, at the time T, is basically the mean surface temperature plus a periodic term that quantify the cycle, and the cycle is have an amplitude as, right, times a sine function, and the sine function is like 2 pi t over p. So this is basically you know, like if 2 pi t over p is basically the cycle, right, the cycle. Yeah, for instance, if t is exactly 1 day, then the whole term is just 2 pi. So it has finished one cycle, all right? So this is, you know, t over p is, you know, this is, yeah. So this would basically be the top of the soil, right? So if I have to draw it, it would be somewhat like, you know, if this t, all right, then if this is ts, yeah, then it would be something like, yeah, something like that, yeah, something like that, okay, all right. So ts, and this here is the amplitude, all right. No. This here is blah, blah, blah. Yeah. So I would rather not meddle with my own math. Okay. So you know, like this here is the amplitude, right? This here is the amplitude. Yeah. So like this here. So this here should be the amplitude. Okay. Yeah. Yeah. So yeah. So let's say this is a boundary condition that we give to the solution, and this boundary condition has a cyclical shape because we know that the surface temperature is shaped by diurnal cycle of solar heating, and we idealize it by just using a sine function. Okay. In reality, usually no, it's not exactly a sine function. Okay, and then we basically do never really analytically solve anything. Yeah, we always use numerical methods to solve things. But let's look at this idealized situation, because this idealized situation actually gives us a lot of insights. So if you solve it, soil temperature as a function of depth, z, all right, and of course as a function of t, is actually this, the surface temperature plus as, which is the amplitude here, times an exponentially decaying function. So the decay actually goes with d, which is some kind of depth, okay? So the deeper you go, or the damping depth, sorry, as a function of z. So if z is higher, meaning it is at a greater depth, all right? At a greater depth, then let's see. Yeah, I think here z is defined in terms of the deeper it is positive. Okay, so yeah, not too good. Actually, I don't like that coordinate system. But anyway, so z here is actually I think yeah. So the deeper you go, it is positive z. Yeah. So anyway, so remember that z is actually positive if you go deeper down. So if you go deeper down, the amplitude is actually smaller. All right. And then you also follow a sine function because, of course, there's solar forcing, and then you should have some kind of periodicity in your even if you go deeper down. But the amplitude is actually smaller, okay, if you solve the equation, all right? And very interestingly, there would be some shifting of the cycle as well, all right? The peak would actually be shifted a little bit, all right, actually later. Yeah, indeed, this is a theoretical solution or analytical solution to this equation here, given a particular boundary condition. And then this boundary condition would exactly, or sorry, I shouldn't say exactly, it's not. This solution can actually capture a lot of the temperature changes in reality, capturing the two most important feature. First, the amplitude of fluctuation actually decreases with depth, right? Defining z to be positive if you go deeper down. And the peak actually shifted later, okay? So it's very cool. Here, d here is what we call a damping depth, okay? kind of like a scaling height. If you remember from atmospheric dynamics, you have scale height, right? This is kind of like scale height, but here we're talking about a damping depth, okay? So the rate of decrease of the amplitude, okay, with depth. So the damping depth is quantified by alpha period divided by pi, okay? And the damping depth itself, and alpha here is basically this term here, okay? All right, so basically this constant, this rate, alpha, we call it the thermal diffusivity, all right? So this whole term here is called thermal diffusivity, okay? And you would have the damping depth, okay, here and there as well, all right? And Z here is, yeah, positive. Yeah, so I should really mention that. I should really say out loud here, yeah, to make sure everybody get this Z. Yeah, okay, and larger increases if you go deeper down. Increase. Yeah. Yeah, so Z decreases downward, okay? So Z is not negative here, all right? All right. So amplitude decreases with increasing depth, okay? So a key feature, good. And indeed, at about 3D, okay? Like 3 damping depth, all right, 3 damping depth, then the amplitude is just about 5% at that of the surface, right? So isn't it cool? Basically now, you know at what depth would temperature be not changing that much anymore, okay? Well, it's an exponentially decaying function, so it will never really reach 0, okay? But you have to define somewhere, you know, which is like when the amplitude is small enough that you say, okay, we forget what happens next, okay, deeper down. So let's say 5% is roughly where you want to look at, right? Roughly, and we know that at about 3D, it would be it. So how deep is it? Well, I mean, you just substitute a number, right? You have the period here, you have the alpha here, depending on the soil, okay? And you will have a pi here. And you will see it is basically less than a meter. Yeah, I think it would be less than a meter. Okay, and this obviously capture this very important things. The amplitude actually goes down. And as soon as you go down to about 40 centimeter, it's already not changing that much, okay? So good, this theoretical model explained the profile pretty good. Well, I mean, not exactly, but you know, schematically, it is good. And most importantly, if you look closer at it, okay, if you try to plot it at different Z, you can also see that the maximum temperature also appears later than at the surface, all right? There's some shifting of the whole cycle. And the peak temperature actually shifts by about Z times P divided by 2 pi D, all right? You can substitute here, okay? All right, ZP divided by 2 pi D, okay? And then the whole thing is just basically a 1, or yeah, I think 1. And yeah, relative to that at the surface, okay? So this, you can try to substitute it here, time t, and then, yeah, compared to, you know, another time t, and then you can really see this is the amount of time that the peak would be shifted, okay? And if you plotted this curve over at different depth, you can actually see something that is similar to this, and the shifting of the peak. All right, so great. This theoretical model can explain some of the features very well. So here, another question for you to look at, to work on. And I would like you to think about it a little bit as well. Okay, and basically this question, a moderately wet soil has a thermal diffusivity of this thing. All right, this is already the alpha, by the way, it's already alpha. over the course of a day, what is the soil depth at which amplitude of temperature fluctuation is reduced to only about 5% of that at the surface? And what about over the course of a year? So if the period is different, let's say we're looking at seasonal cycle instead of diurnal cycle, then the period is totally different. The period is a year instead of a day. Then what would be the depth at which there would be no more seasonal fluctuation or very little seasonal fluctuation? Okay, right? So there are two time scales: diurnal cycle, right? And then there will be a diurnal fluctuation, and at a particular depth, there will be the diurnal fluctuation can be ignored. And for the seasonal cycle, all right, there will be a huge amplitude of seasonal cycle, obviously. But again, at some particular depth, there will be very little seasonal cycle anyway. Okay, so try to work on it. All right, given this, and then it gives you actually a pretty good idea about what the soil is doing. Yeah, on a seasonal time scale versus a daily time scale. All right, so try to work on it. And if surface temperature peaks at about 2 p.m. in the afternoon, okay, back to the diurnal cycle, okay, when does the peak temperature occur at a depth of about 20 centimeter, all right? So this is good, right? Like the top soil peaks at 2 p.m., then you can actually calculate when does the peak temperature occur at a depth of 20 centimeter, okay? Try to apply, what we have just seen before. And as the soil becomes drier, will the damping depths increase or decrease, okay? And why? Please think about it, all right? And this only requires some words. So if you know what right away, you can also just send me the group chat, send the answer to me in the group chat. I think the calculation would definitely require some time, but if you know the qualitative answer right away, you can send the answer to me in the group chat as well. So again, I would like to give you just a little bit of time to digest the question and to think about it for a few seconds. All right, we'll cover it later, but yeah, I don't want to. Yeah, okay. So pause recording. All right, so let me continue. Yep, and clear all drawings. Okay. So yeah, so that is basically like a really cool way where you have, the analytical solution, and the analytical solution is really capturing some of the basic, really basic, important features of what is happening to soil temperature over a course of a day, and also over the course of a year as well, indeed. So that is really cool. So yeah, but in reality, usually, well, the soil is usually not homogeneous. And the forcing itself is not exactly a exactly a sinusoidal function. So oftentimes we just have to numerically solve it. I mean, in reality or for practical purpose, we do have to numerically solve for the solution. But the analytical solution is great. All right, it explains a lot already. So yeah, but there are other complications because soil is really not homogeneous. There can be organic matter, snow, and things like that. So organic matter, like humus, for instance, and snow have really low thermal conductivity. And thus, they can actually really act as an insulator and reducing the amplitude of the diurnal or seasonal cycle of soil temperature. All right, so if a forest is particularly productive, usually there would be a lot of humus, not hummus, hummus is a food from Middle East, okay? Humus, yeah, those usually really help insulate the soil, such that the soil can have relatively regular temperature or the fluctuation would not be too high. Okay, so organic matter has this particular property. And snow would have the property as well. So snow covered soil also is kind of insulating. Okay, so it doesn't change much temperature over the course of a day or yeah. But there are some important things going on for snow. So phase change, if the snow actually is actively melting or forming, right? If it is like melting and forming, so to speak, for instance, after snow, and then it is, let's say it is still very cold and it's still covered by snow. The snow is not melting, it doesn't matter. It's very insulating. But if the temperature is above, say, 0 degrees Celsius and the snows are melting, Then the phase change of the snow, the freezing and melting of the snow, soil water basically can really buffer the effect of external thermal forcing as well, right? You can imagine maybe after winter, the spring is coming, okay? And then the sun is growing stronger and stronger, and then it is melting the snow. But the temperature of the soil itself, if this soil itself, may actually not fluctuate too much diurnally, because because of the snow is actually taking in a lot of the heat in order to melt itself. Okay, so a lot of the heat is taken up by the snow melting, all right, as a form of latent heat, and thus not really reaching the soil particles and changing the temperature. So phase change can further buffers the effect of external thermal forcing. So you can see that bare day, litter day. Yeah, so this is like organic soil. You can see that bare land, so bare land, so bare land can have really large diurnal cycle. But then if you have a lot of litter, then the diurnal cycle is actually very small, okay? And at the same time, for instance, with phase change and without phase change, okay? So the temperature, the temperature at a particular depth over the course of a day, with phase change, it would be changing this much, but without phase change, it will be changing actually a lot more. All right, so again, phase change can take up part of the heat. So this is just that. And if you don't mind, I would like to briefly go to the next lecture first, because if you don't mind, because I want to make sure that during next lecture we would have enough time for the question. Okay, if you need to go now, feel free to go. But I would like to continue a little bit, maybe for 15 more minutes, if you don't mind, because I want to make sure that we will have enough time to cover the exercises next lecture. Okay, so if you need to go, please go now. And you can watch the video later after now. Okay, so don't worry about it, or you can stay with me. So if you don't mind, I would like, actually I thought the class is until 5:30, so I planned that to happen. Sorry about that. If you need to go now, but you can watch this 15 minutes later. Okay, so you're sharing the screen. Yeah, so so next lecture, or I'm going to start this lecture now. We will go over hydrological cycle, soil water movement and infiltration, something that is very related to what we have covered today, and also evapotranspiration and water balance model. Basically, the concepts that are very important for understanding the movement of water on land, and how that would affect meteorology. Okay, so I'm going to start a little bit now. So first of all, I have to stop share and find the right lecture. And share again. Okay. So now let me get the second lecture started for about 10 more minutes now. Okay, I hope you don't mind. If you need to go, you can go now. Okay, and you can watch this 15 minutes later. So we have talked about soil, and we will come back to soil again. To understand soil water movement, we know the context is that soil water movement is part of the larger hydrological cycle, a part of it and a very important part of it. And there will be other parts of the water hydrological cycle that we're going to study more, including evapotranspiration and things like that. So the hydrological cycle is very important for climate, obviously, because climate, as you have learned in other classes as well, water plays an important role in shaping meteorology and climate and atmospheric chemistry, because it is a chemical species that interact with other things. It is a form of latent heat. So, its phase change actually really affect the thermodynamics of air, and water obviously is part of the precipitation and things like that. So very important. So the water cycle basically have many important processes. We will go over all of them actually, and specifically focus on some of them more mathematically. So, well, first of all, it starts with precipitation, obviously, because that's usually how we perceive water cycle, right? Rain falling, okay? Let's start there. So rain would fall. After it falls, what happened? Some of it would actually be intercepted, all right? Intercepted, I'm going to go over it. Intercepted meaning it just fall on some surface and get stored in those surfaces, okay? Maybe the trees, the rocks and things like that, okay? Some would start to, the intercepted water would start to, some of it would start to evaporate right away, okay? As long as rain falls, some of it is bound to evaporate right away anyway, okay? But some of it actually to go, don't just stay on the trees. Some of it would go through the tree, okay? Through fall or stem flow. We'll look a little bit more of that, all right? And reach the surface, okay? All right? And as it reached the surface, some of it, of course, would still evaporate, but some of it would actually go down to the soil. So going down to the soil, the process is actually called infiltration, okay? We'll spend quite some time on infiltration. Some of it is just stored on top of the soil. We call it depression storage. And some of it, if the rain is too strong, then if the soil is over its infiltration capacity, some of the water would just go above the soil, right? Ponding would occur, and then some of it would just run over the land surface. We call it overland flow, right? Or runoff, or simply runoff. So, and some of it, but then some of it that infiltrate downward, some of it would actually become groundwater, and the process of infiltrated water becoming soil water, becoming groundwater is called percolation. All right, percolation is kind of like the recharge of groundwater. All right, basically water going down to form groundwater. During the time there will be redistribution. We are going to learn a little bit. Redistribution is kind of like some water may actually go being sucked back up to the surface because of a suction. All right, suction by the plants, suction by evapotranspiration. So some water would actually go back up. Some of them would take up by the plants and then be transpired by the plants through transpiration. So that is actually very important because the land is mostly vegetated. Okay, yeah, transpiration is extremely important for among evapotranspiration. So plant uptake and transpiration. But some of it, some of it still have interflow, groundwater flow, and ultimately becoming part of the lake and things like that. And some of it would go into the ocean through river runoff, river discharge, runoff and the river discharge. And throughout all of these processes, there would be evaporation. So yeah, evaporation is just like constantly occurring, and transpiration together with transpiration, that basically put water back to the atmosphere. And again, if they condense, they would form precipitation. So that would so to speak, complete the water cycle. But the water cycle actually has all of these processes, okay? It's not just evaporation, runoff, and things like that. But I mean, there would be a lot more these things. But we can, later, you can group them into a specific term and try to quantify them collectively. So the hydrological cycle powered by the solar energy can be considered the master cycle driving all other geochemical cycles. Okay, so yeah, that would be, that's why the hydrological cycle is very important to understand. So this class, even though I call this part hydrometeorology, which means that I should talk more about precipitation, but no, I'm not. This class would not be too much about precipitation. Precipitation would definitely, the rain, cloud and rain formation definitely deserve its own course, okay? And I think Manin would really like to teach it as well, okay? So here I'm just going to go through to be complete, okay? To go through different kinds of precipitation that are important for atmospheric purposes. So I would actually go here first because this is usually how we, or common people understand precipitation. People generally think of precipitation as, oh, okay, air rises. and the water vapor in the air would becomes cooled down and then condenses and then rainfall. That is really only one form of the three major forms of precipitation. We call it convective precipitation. Okay, so simple, right? Like solar radiation hit the ground, air rises. As air rises, we know that it has to cool adiabatically. And upon adiabatic cooling, the water vapor in the air would at one point condenses, would one point condense to form clouds. And the clouds droplets would coalesce with each other to form larger and larger droplets until one day the convective updraft is not strong enough to hold the large water droplets, and the water droplets drop, right? And then that will become rain. Okay, I would just mention that, well, actually clouds are water droplets, right? They are definitely denser than air, but clouds stay in the sky. Have you ever thought about why? Why would clouds stay in the sky, even though they are water droplets and they are heavier than air? They are denser than air, right? Have you thought about that? Okay, they're not gas. They're actually they're denser than air. So clouds stay in air really because within the clouds themselves there is very rigorous convection going on. There is constantly turbulence and instability and convective updraft, basically air rising. Air basically keep rising within the cloud column, okay? And the rising air basically give buoyancy to the water droplets, to the cloud droplets, so that the cloud basically stay there in the air, right? Instead of falling. But you know, if the cloud droplets coalesce to form larger and larger droplets, then at some point, even the convective updraft buoyancy cannot hold this anymore. So at that point, it rains. So yeah, so clouds and rains are really like a continuum of things, okay? Rain occurs when the convective updraft is not strong enough to hold the cloud anymore, and then it falls, all right? So, but then that is really only one form of rain. And that form of rain is most common in, in summer, and also in relatively subtropical or tropical areas, okay? So it is very common in Hong Kong in summer, all right? Another form of precipitation is frontal precipitation. So this is actually not caused by convection at all. It's basically when two air masses of different temperatures come into contact. And in France's class in atmospheric dynamics, he would definitely talk about cold front and warm front, and I talked about a little bit in climate system dynamics as well. So basically, warm front, cold front are really part of the synoptic scale extratropical cyclone system, all right? Synoptic scale weather system, okay? And basically, that is really large scale dynamics, okay? And then the larger scale dynamics would then have microscopic, well, I shouldn't say that, more regional effect, which is, for instance, if there is like a warm front, warm air sliding over cooler air along a warm front, okay? Then the warm air usually have a lot of water vapor. And then the water vapor basically just meets a very cold air and suddenly just, condense. And then there will be rain. So it's basically just warmer air containing more water vapor meeting cold air, and there will be rain, okay? Usually, because warm air advances over cool air less dramatically or less fast than cold air advancing through warm air in a cold front. So usually the rainfall in a warm front is milder, right? So again, well, it's very qualitative, but a lot of it is very qualitative in a sense, very hard to calculate anyway. So the phenomenon is that warm front, usually the rain is milder because warm front moves only relatively slowly past a cold air. So the change in temperature and everything is not that dramatic. So it's relatively mild, okay? Usually a lot of relatively mild rain, okay, over a very large area. And if you see the sky, if the whole sky is covered by overcast, sorry, the whole relatively uniformly, then that is usually the frontal precipitation. Okay, we also call it stratiform precipitation. Okay, maybe I should really draw this word as well. It's also called stratiform precipitation, right? Okay, all right. So, but on the other hand, usually cold front would advance through a warm front, cold front. In a cold front, the cold air usually advances much faster and more rigorously towards the warm air. Okay, so usually when the cold air really undergo sort of like a sweep under the warmer air, it usually causes convective motion as well. Okay, because suddenly it becomes very cold, and then it is and then the air here really rises up very quickly over the cold air beneath it, and then forming a lot of rain there as well. And usually this situation is associated with thunderstorm. Okay, so there would be thunderstorm, there would be you know, like maybe even snow. Okay, in a temperate region, it would usually be associated with snowing as well. Okay, so very rigorous, usually a lot of thunderstorm and things like that. All right, so because this is yeah. And the final form, okay, I'll stop after this slide. Okay, the final form of precipitation is orographic precipitation. It has nothing to do with, well, very little to do with synoptic scale phenomenon or convection, which is mesoscale. This is synoptic scale. This is really just like, you know, when air has to be forced up a mountain. We know that when air is forced up a mountain, then it has to adiabatically cool down, and thus water vapor can condense and form clouds. So on what we call the windward side of a mountain, all right, meaning that the air is going up the mountain. The windward side meaning the marine air usually go up the mountain. Then there will be a lot of rain, right, formed on the windward side of the mountain, right? It's because you know, the air is flowing toward the mountain, and that it is lifted up because, you know, the orographically, you know, topographically, it has to be forced up, and then it cools down and rain. Okay, and once it gets to the top, usually they are forced down again, right? Because of course air has to go somewhere. But as it falls down, well, it adiabatically warms up and expands. Okay, so it becomes warm and dry. All right. So usually we call it the leeward side of the mountain. All right. So usually the windward side would be very rainy, and the leeward side would actually be very dry. Okay, very dramatic differences between the two sides. So, and this rain, we call it orographic rain. Okay, or orographic precipitation. Mountains forcing air masses to be uplifted until saturation is reached on the windward side of the rain. Okay, so these are the three major types of precipitation. And I'm sorry, we're not going to talk about precipitation much. And then usually, for the purpose of boundary layer meteorology, we just take the precipitation as a given, okay, and look at how they shape the soil moisture and evaporation and things like that. Okay, boundary layer meteorologists usually don't really look at the process of precipitation. All right, so there are some other people who look at it. Okay. All right, so sorry again for keeping you for 15 more minutes. I think that would be the way to do it, because I want to make sure that you don't have a separate tutorial session. So I want to make sure that tutorial, we can have enough time for the tutorial, okay, on Thursday, okay? All right, so thank you, and I'll see you on Thursday. And I can still stay here a little bit and answer your question, okay?